Welcome to this explainer. Okay, I want you to close your eyes for just a second. Imagine we're stepping into this incredible, futuristic chemistry laboratory together. Seriously, picture it. All around us, floating right in the air, are these glowing metal ions in deep blues and neon cyans. And they're surrounded by these colorful, complex molecular structures that are just snapping together like high-tech magnets. It looks like science fiction, right? But what we're visualizing is actually the breathtaking reality of coordination compounds. This chapter is literally the absolute backbone of modern inorganic chemistry.
So let's dive right into this. Have you ever wondered why certain chemical complexes give off this brilliant, glowing light? Or, why some of the most precious stones on Earth look the way they do? Well, that is our mystery box for today. We're going to uncover the invisible architecture that makes these futuristic complexes tick. And more importantly, we're going to see how we can understand them at a totally fundamental level.
You see, those incredibly vibrant reds of rubies or the deep, rich greens of emeralds, they aren't just simple rocks. No way. They are actually beautiful, three-dimensional coordination complexes that are operating with these almost holographic-like energy effects right inside the mineral structure. It's wild. By the end of this explainer, you're going to know exactly how those colors are generated at the subatomic level.
All right, here's our roadmap for today. We're going to cover a welcome to coordination chemistry, the language of ligands, geometry and molecular isomerism, valence bond theory, crystal field theory, and finally, how to crack those board exams.
Kicking things off with Section 1, Welcome to Coordination Chemistry, featuring Werner's theory.
So back in 1898, a Swiss chemist named Alfred Werner essentially hacked the code to these glowing structures. He realized something huge. Transition metals don't just bond in one standard way. They actually have a dual nature. He proposed that metals show two very distinct types of linkages. On one side, we've got primary valency. This one is ionizable, it's satisfied by negative ions, and it basically just represents the metal's oxidation state. But on the other side, we have the secondary valency. And guys, this is the real game changer. It's not ionizable, it can be satisfied by neutral molecules or negative ions, and it dictates a perfectly fixed coordination number for the metal.
Moving on to Section 2, the language of ligands.
Okay, to truly understand how these secondary valencies create such intricate 3D shapes, we need the right vocabulary. First up, the coordination entity. I want you to picture this as a massive, high-tech space station floating right here in our cinematic lab. It's made up of a single central metal atom or ion that is securely bonded to a very specific, fixed number of surrounding ions or molecules.
At the very heart of this space station is the central atom or ion. Think of this guy as an incredibly powerful magnetic core. It acts as the anchor, right? It literally draws in surrounding molecules from all different directions and locks them down into a highly rigid, definite geometrical arrangement.
And the molecules being drawn in? Those are the ligands. Think of ligands as futuristic spaceships docking perfectly into that central core. They can be simple ions like chloride, or more complex molecules like ammonia or water. And together, the central atom and its newly docked ligands are protected inside what we call the coordination sphere. Oh, and a quick pro tip. We always enclose this sphere within a square bracket when we're writing out chemical formulas.
Which brings us to Section 3, Geometry and Molecular Isomerism.
You see, these docked ships, they don't just attach wherever they want. They follow really strict spatial laws. Depending on the coordination number, which is just the total number of ligand connections, the complex forms a specific 3D shape, known as a coordination polyhedron. So, if we visualize a central metal with exactly 6 ligands, it snaps into this stunning octahedral shape. If it has 4 ligands, it typically forms either a tetrahedral or a flat, square planar geometry. Just imagine these structures slowly rotating in front of you, perfectly balanced, perfectly symmetrical, and glowing with energy. It's honestly beautiful. Now, because these structures are so incredibly specific, there is a very precise way we have to name them. When we're dealing with IUPAC nomenclature, the golden rules are simple, but you gotta be strict about them. Inside that coordination entity, you always list the central metal atom first. Then you list the docked ligands in strict alphabetical order. And yes, that's regardless of their charge. Sticking to this step-by-step formula is an absolute must-have skill for keeping everything perfectly organized for your exams.
On to Section 4, Valence Bond Theory, or VBT.
So what invisible forces are actually holding these beautiful geometries together? Well, it all comes down to magnetic properties and orbital hybridization. Transition metals have a trick up their sleeves. They can use either their inner d-orbitals or their outer d-orbitals for hybridization. If they use the inner n-1 d orbitals, they form an inner orbital complex. This basically forces electrons to pair up, resulting in a low-spin, often diamagnetic, complex, like the cobalt-ammonia structure you're seeing here. But if they use the outer end orbitals, it becomes an outer orbital complex, leading to a high-spin paramagnetic complex, like the cobalt fluoride one. Seriously, memorizing this distinction is an incredible hack for your tests.
Next up, Section 5, Crystal Field Theory, or CFT.
Okay, while valence bond theory is awesome for predicting shapes, it totally fails to explain our glowing mystery box from the very beginning. Why do these complexes glow with such vibrant colors? Enter crystal field theory. This theory treats ligands as point charges. When these negatively charged ligands approach the central metal ion, they cause this massive repulsion against the metal's d-orbital electrons. And because the ligands approach from very specific angles, they don't repel all the orbitals equally. This causes the previously equal, or degenerate, d-orbitals to aggressively split apart into two distinct energy levels. We get a lower tier known as T2G and a higher tier called EG. Picture these tiers breaking apart like vibrant, glowing shelves of energy.
And here is the cinematic payoff we've been waiting for. When white light hits the complex, an electron down in that lower T2G level can absorb a very specific wavelength of light to make a slow-motion jump up to the higher EG level. Because it absorbs that specific wavelength, the light that actually passes through, the transmitted light, produces a vivid complementary color. For instance, the titanium water complex absorbs blue-green light to make this exact DD transition, which causes the complex to radiate a striking violet color. This dynamic splitting is literally the exact same process that gives rubies their red and emeralds their brilliant green. How cool is that?
Finally, Section 6, Cracking the Board Exams.
Now that we have the architectural blueprints and the energy dynamics of these futuristic molecules down, let's shift into high-gear test prep mode. Take a look at this question straight from the NCERT text. It's asking which ion has the highest magnetic moment. So the crucial point here is that a magnetic moment depends directly on the number of unpaired electrons. By applying what we just learned about oxidation states and orbital configurations, it's actually like a giant puzzle. We simply figure out which metal center, chromium, iron, or zinc, has the most unpaired d electrons in its specific oxidation state. It all comes back to that foundation.
To really lock this in, let's quickly review our 4 foundational pillars. First, master the difference between Werner's primary and secondary valencies. Second, memorize those strict alphabetization rules for IUPAC naming. Third, know exactly how to contrast inner, low-spin VBT orbitals with outer, high-spin ones. And finally, always link the magnificent colors of these complexes directly to crystal field theory and those subatomic d-d electron transitions. Keep these structured in your mind and you are golden.
As we step out of our cinematic chemistry lab today, I want to leave you with one final, provocative challenge from the NCERT text. Look at these 3 nickel complexes. Based on what you now know about the spectrochemical series and how different ligands cause different levels of orbital splitting, what do you think will be the correct order of the wavelengths of light they absorb? Think about those energy gaps. I'll leave that mystery with you to solve. Keep exploring, keep questioning, and I'll see you in the next explainer.